Our last lesson is on balancing register allocation across threads, specifically across network processing applications. Modern network processing applications execute in tandem, sharing the data across them, and also context switching to maintain high throughput. Unless one manages the context switch, one will pay a huge latency price. Context switch is encountered upon hitting a memory operation. So register allocation should be sensitive to the other executing threads and must be carefully managed and orchestrated by the compiler. So students, having seen one type of register allocator for network processors which facilitates dual bank register allocation, now let us take a look at yet another big problem that occurs in network processors, namely register allocation across threads. As you know, the packet processing happens to take a lot of cycles and must be really fast to keep up with the line speeds. On the other hand, we have increased CPU and memory gap, and the way the network processors have approached this problem of very fast packet processing at line speeds and tackling the CPU memory gap, it is as follows. On one hand, they deal with parallelism so that they can do lots and lots of packet processing in parallel. So each packet is independent, so they exploit parallelism. The parallelism is at the level of multiple threads, and there are multiple instances of microcores inside the network processors. So this is how we exploit parallelism at multiple levels. One is at the packet level, second is at the thread level. Now in order to deal with the memory and CPU gap, which could be about thousands of cycles, what the network processors do is they do a context switching. Upon encountering a memory operation, the network processor switches a thread and schedules the next thread for processing. And this context switching is very lightweight. There is no OS involved, there is no context saved, and therefore it is extremely fast and has almost zero overheads. And so in this setting, when the threads are scheduled upon a context switch for load or store going to the memory, and then the context switch taking place without any OS, how can we minimize the context switches and how can we improve the thread throughput? That is the question that is tackled in this particular lesson. So on the previous slide, I mentioned several concepts all at once. Some of them are well known, such as the gap between CPU and memory. Some others are also well known, such as what exactly is a context switch, that is saving the system state and reinitializing with another system state and resuming the execution in that particular state. That is a context switch. But some other concepts are probably new here, and let us make sure we understand and reinforce them before we move further. So the new concept that I introduced is threads. So what exactly is a thread? I'm sure many of you use threads such as pthreads in your Unix and Linux type of operating systems and have done a lot of programming using them. But let us quickly understand what exactly a thread means. So I have a small quiz here for you. In this particular quiz, I'm giving you some choices here. Please mark the answer that is always true. So the first statement is, on a multi-core system, one of the cores is designated as the master and schedules the threads for each other core. Is this always true or not? The second one is, a thread is the smallest sequence of programmed instructions that can be managed independently. And the third one is, threads do not share memory, executable code, and context. Again, please make sure you mark only those statements which are always true. Please go ahead and mark your answers now. So let's look at the first answer. On a multi-core system, one of the cores is designated as the master and schedules the threads for other cores. Is this always true? The answer is no, not really. Some systems, that could be a setup that there is a one master and others are slaves. In many other systems, all the cores are exactly identical and are symmetric and there is no concept of a master. So this statement is not always true and therefore it is not marked. Let's go to the second one. A thread is the smallest sequence of programmed instructions that can be managed independently. Is this always true? Yes, this statement is always true because regardless of how they are scheduled, who initiates them, who manages them, the thread as an entity is a sequence of instructions that is managed as an entity. And so this particular statement is true. The third one, threads do not share memory, executable code, and context. This is not really true. Many threads in fact do share memory, do share executable and so on, and therefore are allowed to share some resources such as memory, even some code, and so on. Now, having introduced what exactly is a thread, let us see how they are managed in terms of the scheduling by different processor architectures. So we have here different diagrams in terms of what exactly threads are doing and how they are being scheduled. And the color code shows that those are the groups of threads that belong to a given application. So in other words, different applications are concurrently executing, and the architecture is managing these threads corresponding to different applications by scheduling them. And the way they are scheduled is shown by these colors in these diagrams. And what we are asking you to do is to name different architectures that are managing these threads in different ways. So here is a list of architectures that we have. Fine-grained multi-threaded scheduling. So try to put this in front of the right thread scheduling policy here. Conventional processor, the way it manages multi-threading, please write it in an appropriate box, either here or here or here or here. Then we have simultaneous multi-threaded processors or simultaneous multi-threading in terms of scheduling decisions. How it takes those decisions, again take a look at these diagrams. Again, the threads of a particular color belong to a given application. Threads of a different color belong to another application, and then the architecture is scheduling them. And then finally another variant, coarse-grained multi-threaded architectures. How does scheduling of threads looks like on those? Try to fill that in the appropriate box. So please go ahead and write your answers as per the scheduling policy that you see in action in terms of these threads and match it with the processors on the left-hand side. Please go ahead and write your answers now. Now let's look at the answers starting from the top. What is going on here? An answer is this is the way the conventional processor operates. Why? Because see what is going on here. The thread 1 is scheduled, and then there is an interrupt, an OS call, and the thread is descheduled. Once the operating system takes over, it does certain processing, and then it goes ahead and schedules the other thread, and that is now scheduled over here. So there is, between the different threads, there is a conventional OS call which is doing the scheduling and change of context and other things. So this is what happens in a conventional processor. You can imagine now how much overhead it has, because between the thread schedules there is an intervening OS call, and that could consume a lot of cycles and time. The second one, the exact same thing is going on as in the first case, except that now the reasons are very different. The reason is probably a cache miss, which could be a high latency operation, and different threads then execute right after each other, but then they are not going through an operating system call here, and they are going into action because of an architecture event such as a cache miss. So in other words, this is also a coarse-grained operation because the thread is executing for a particular amount of time, and then when a hardware event occurs here, the context is switched and a different thread is scheduled over here. So this is what happens in the CMTs, coarse-grained multi-threaded operations, and the schedules look like one thread executing for a few cycles, then another thread executing, then yet another thread executing, and so on. Now, let's go to the third one. What is the difference between the second and third one? You can see that each one of these threads is now getting a very small amount of interval of time, and then is switching to the next one, switching to the third one, fourth one, and then back to the first one. So this kind of round-robin policy, which is implemented at a very fine-grained level, which is giving a very small amount of time for each thread, and then switching it to the next thread, is called as the fine-grained multithreading. So you can see that in FMT or fine-grained multithreading, even though a thread is scheduled on a given core, there is a bit of cycles here where the thread is really idling. So the question is, can we fill it up with another thread? And when we do that, it is called as simultaneous multithreading. This is also called as hyperthreading in commercial architectures such as x86-based Intel processors, wherein two threads are executing simultaneously on one core. So green and red are executing together, blue and yellow are executing together, and so on. If we do this particular scheduling such as this, you can see that we can pack much more useful work in a shorter span of time, and that's why SMT or simultaneous multithreading is very popular in practice. So the question is, which of these styles do the network processors embrace? Obviously it is not this because there is no OS. Could it be this? or this. And the style that is embraced here is coarse-grained multithreading, which is embraced by the network processors. After a thread executes for few cycles, there is a cache miss which could cause a latency, and immediately another thread is scheduled there. During this particular time of execution of second thread, the first thread is completing its latency operations, getting the data from the memory and so on. And once again, when it is ready, it is scheduled over here. By that time, other threads could go through their cache misses, and therefore the cache miss latency, which could be hundreds of cycles because of huge memory and CPU gap on network processors. That's how the gap is bridged here. You may ask me, why such a big gap? Obviously, the network processors clock at gigahertz frequencies, and the memory speeds at most are few hundreds of megahertz. So let us look at the multithreading context switch that occurs in network processors. First thing is the scheduling in the network processors is completely without any OS involved. It's purely using the hardware, which wakes up the next thread, and it exploits the independence amongst the threads. So in other words, many threads are executing here. The higher the number of threads execute, the higher is the throughput, which is really the aim in network processing, because it's a streaming type of a processor in which the packets are streaming in and they have to be streamed out at the line frequencies. Otherwise, the whole thing will not work. The buffering will exceed any allowed buffer size, and therefore the system will fail. So usually you have 4 to 6 threads for each processing unit, and they assure you a very high throughput. As I explained earlier, when a particular threads run into a memory operation which could have a high latency, it is descheduled and the next thread is woken up and is scheduled, and that occurs in a round-robin manner. So the latency hiding really is performed for hiding the long latency instructions such as memory read, writes, hashing, CAM memory, and so on. And lots of high latency operations can be hidden. In fact, as small as 20 cycles can be hidden because the scheduling overhead is 0. Let us now see through a simple example how the multithreading works as far as the context switching is concerned in a network processor setting. So here is one thread that we have which executes, and here is another thread that we have which executes. And let us see the thread interactions here in terms of scheduling that takes place here. So the first thread starts scheduling here at the first operation. So after the thread is scheduled here, it executes the first operation, then the second operation, and then it goes and starts executing the third operation. Note what the third operation is. It's a read, and that causes a context switch because the read is going to take a while. It will have a latency of 100 or thousands of cycles depending on where the data is, and therefore this thread is descheduled at this particular point, and the control goes to the next thread in terms of the execution. And then the next thread is scheduled and it starts executing. It executes the statement x is equal to 6, and again that runs into a read operation which could take thousands of cycles. And at this particular point, again there is a context switch. The control comes back to the first thread, and by this particular time the value of C hopefully is read from the memory, is ready, and it starts executing this C. Once it completes this C, this goes to D, and at a later point again there is a context switch. The control comes back to read of C which would have completed, and then after that the execution resumes along W and so on. So as you can see here, the first read leads to a context switch going here. It executes x is equal to 6. Then it leads to a context switch. The control comes back here. The read completes. The things start executing further. Again, there is a context switch. The read completes. And the W onwards, the second thread starts executing. So you can see here that the moment the read or write operations are encountered, the thread is descheduled and the other thread is scheduled. So useful work is done during the load store operations in network processors, and that's the way the latency is hidden. So let us understand the context switch instruction in general in the network processor. So the first is the context switch is done only when the long latency instruction is executed. The second one is the threads are non-preemptive, predictable, and this is tied to the instructions. In other words, the context switch is not random, but actively takes place at the places where there is a long latency operation, or there is an explicit CTX instruction which is executed by the network processor. And so one could context switch very frequently in network processor because it is a lightweight context switch where the PC is the one which is saved. It just takes one cycle, nothing else is saved here. The last one is very, very important part of the context switching. You can see that is very, very lightweight because only PC is saved and nothing else is saved, and therefore it is the application's job or the compiler's job to manage the context switch properly so that the state is not really lost. And if we are not careful, the state of a particular thread, which may be in registers, will be lost upon a context switch because the second thread would go ahead and overwrite it. And the last part is the real motivation for this particular work. In other words, how do you manage the state across the context switches through registers? Let us now see what really exactly happens between a context switch, especially with regard to the interactions between the threads. So we are showing here two threads which are executing certain functions and so on, and their execution paths are shown over here. Thread A is marked in yellow and thread B is marked in red. And based on this, please select the answer that are true on the right hand side. The first statement is all code is accessible by all the threads. Second one is you cannot make assumptions about relative ordering between two concurrent threads. And then the third one is each thread has its own stack for local variables and its own heap. So please go ahead and mark your answers which you think are true, especially about the thread interactions shown here. So all the code is accessible by all threads. That is true because the thread can really select the part of the code it executes by using its thread ID, but all code is as such accessible and is shared across threads. The second one is you cannot make assumptions about relative ordering between two concurrent threads. Is this true or false? This is also true because threads are independent entities and they do not have any ways of ordering in terms of which executes before what as such, and that's why this statement is true. And the third statement is each thread has its own stack for local variables and its own heap. That is not true. The thread typically has its local variables on its stack, but the heap is typically shared. So given what we have seen so far, in order to implement a context switch, this is how we could do it in a simple conventional style. We could have a big register file in which we hold the states of all the threads, but we hold those disjointedly. In other words, the thread 1 state is held in a set of registers disjointed from thread 2, disjointed from thread 3, disjointed for thread 4. So let's say if we have 64 registers here, first 16 could be given to thread 1, next 16 to thread 2, the next 16 to thread 3, and the last 16 to thread 4. So how does this solution will work? The registers are disjointed and therefore they are not saved across the context switch, and there is no need to save them because thread 2 will only operate on a set of registers that really don't belong to thread 1 or thread 3 or thread 4. So why this particular solution is not good then? As you can see here, as we increase the number of threads or as we increase the number of registers that are given to each thread, we are going to need larger and larger register file here. And that is going to need larger databases, that is going to slow down the clock cycles, and also going to increase the area on the die to hold the data, effectively reducing the die area for holding the cores or micro engines. And if we do that, then that reduces the parallelism. So on the other hand, a solution which relies on sharing registers, let us see how that would work. Remember, the context switch is very light in our network processors. What it means is only the PC register is saved, but the contents of other registers which hold the data, they are not really saved. So what it means is it is not safe to share registers, because imagine thread 1's part of its state residing in register 5, and that register 5 is now made available to thread 2 without saving it. What will thread 2 do? Thread 2 might override that particular register with a new value. And so when we get back to thread 1, resume its execution after it is scheduled, you are going to see a destroyed value in that register 5, and that means the program semantics will be jeopardized. So the alternative is, if you don't share registers, then you get less number of registers for each thread. You may not be able to fit the data of each thread in those registers. That will cause more spills, in fact more context switches Because remember, every time there is a spill, there is a memory operation, a load or store. That means we are forced to schedule another thread, and that will eventually cause lower performance. And all this discussion therefore brings us to this piece of work which we have in this lesson, which is all about how to effectively share registers across threads in a safe and highly effective manner. So here we have different threads. We could sort of allocate disjointed registers to them. And if we allocate these registers, as I mentioned earlier, we could at most get 64 by 4 registers for each thread, at most 16 registers that could lead to spill and so on. Note that no register is shared across any thread in this particular case. They're all disjointed. Whereas under our scheme, what we could do is partition the pool of registers into two parts. One is private registers, and give each one of those private registers to each one of those threads, just like we do earlier. But then we also have shared registers, a pool of shared registers which we keep here. And this pool of shared registers is what we could allocate and give to all the threads to share, to use them. But then it is up to us to manage them well. In other words, when one thread that is using these shared registers, before it context switches to the other thread, we should save these registers, and therefore we should not cause any overwriting of these registers. And so their management is under the compiler control. And that brings to the central problem that we are solving in this particular lesson: compiler determination and allocation of shared and private registers across threads to maximally meet the register demands. In other words, how to carry out this partition, first of all, of total number of registers into private and shared registers, and then how to allocate the shared registers, and then most importantly, after allocating them across thread switch boundaries, which is at the context switch points, which we know, by the way, looking at the code in terms of read, writes, or CTX instructions, how to manage these shared registers by saving them before the context switch occurs and by restoring them after the context switch occurs. How to perform these actions is really the problem that is solved in this lesson. So how do we solve this particular problem? We solve it in terms of what to put in shared registers in the first place. Note this: the live ranges in shared registers must not reside in shared registers across context switches. Because remember what could happen? If there is a live range which is sitting in R5, and R5 is a shared register and the context switch occurs, this value which is in R5 could be overwritten by the context switch thread, the next thread to which the scheduler chooses. So there should not be any live ranges which should stay in the shared registers across CTX instructions. Upon context switch, they should already be dead, freeing the shared registers, or they should be saved in memory locations, and therefore the context switch, even if it overrides them, has no effect because they could be restored from those locations after the context switch. So the first thing that we do here is categorize the live ranges into two types and allocate them separately. The ones which are live across context switches and the ones which are not live across context switches, we treat them totally differently. One we allocate out of a pool of shared registers, and the second one we allocate out of a pool of private registers. So the ones which are live across context switch ranges, where they should be allocated? They should be allocated in the private registers. The ones which are not live across context switches, where they could be allocated? They could be allocated in the shared registers. So here is the overall framework that we have, therefore, based on this observation. Build non-switch region, that means a region which is between the different context switch instructions, and build the interference graph there. Build also an interference graph across the context switch boundaries. Estimate upper and lower bounds on the number of registers that are needed. Perform the inter-thread register allocation. Perform intra-thread register allocation based on these. In this particular loop, we keep trading private and shared registers, the number thereof that we use in allocation. And finally, we have a solution which guarantees that we are able to share a good bit of registers and we are able to minimize the number of spills. Now, having introduced the overall framework, let us now try to go into details of each one of these phases. So let us first look at how do we build the non-switch interference graphs here. A non-switch region, as it is called, is a maximal connected subgraph of the control flow graph which does not have any context switch instructions embedded in it. In other words, its boundaries are all the context switch instruction, but inside it there is no such thing as a context switch instruction. And why do we build it? The reason we build it is to find out if a live range is entirely contained within this region or spans across such NSRs. Let us see how we can find an NSR. So what we have here is a control flow graph of a particular benchmark from COMBench, which is a commonly used benchmark for network processors. Right at the beginning, you can see here that things which are marked in red, those are all context switch instructions. Why is this a context switch instruction? Because this is a load instruction. This is an explicit CTX instruction, so context switch, which is already present in the program. And then here is another load, which is a memory sensitive or latency sensitive operation, which could take hundreds and hundreds of cycles, and therefore these are context switches. And so what we have in this particular program now is, we have picked up these first instructions, which are context switching instructions, and we have broken the regions, or we have broken the control here before and after. In other words, at each one of these instructions, the context switch takes place, and so the program executes in one particular way, goes here, and then context switches, executes in another thread, and then comes back and starts execution again. Again, that does the same thing over here, and so on. So the region that is existing between the two CTX instructions, for example, between this and this, is one region where the control will stay without interruption in a given thread. Similarly, between this point and this point, the control will stay within this particular thread, or this point and this point, the control will stay within the thread. Between again this point and this point, the control will stay within this thread. So these are NSRs, the no switch regions, where the control is guaranteed to stay. So again, from this point onwards all the way till the end, the control will stay here. So here we see that we have 1, 2, 3 and 4 NSRs which are there in this particular small benchmark. So as per the discussion now, as we have NSRs which are shown in purple color over here. That is one region where the control flow stays within the same processor without interruption, or same thread without interruption. Then we have a red NSR, which is after this particular context switch until the next one. Again, this executes without interruption in one thread. Similarly, we have a third NSR, which is going from here to here, or can go all the way and exit here. And the fourth NSR could be if you encounter the context switch, then after the switch, the control goes back to this thread and again executes this particular part over here. So you can see that in this particular way, we have broken this control flow graph into these different colored regions. Each one of them has no context switch embedded inside it. So if it executes without interruption. What it also means is, if we keep a value which is in a register whose live range is entirely contained within this NSR, then the live range is never exposed to any context switch, and therefore it will always be safe to keep it in a register which is shared. However, we cannot keep that live range which goes across the context switch point in a shared register, because if we do so, then the live range could be exposed to a different thread. That thread could overwrite in it, and therefore it cannot be kept in a shared register, because the shared registers are the ones which could be given to not only this thread but to the other thread as well. So students, having seen these definitions and the terms, please go ahead and write the corresponding letter of the definition in these boxes here. So what exactly is a node? The right answer is B. The node really represents the live range of a virtual register or a variable. What exactly is a boundary node? The boundary node, as you can see here, really belongs to C. The node that is live across the NSBs which may interfere with the other boundary nodes. So a node which is live across the NSR region boundaries is a boundary node, or the live range is live across the NSR region. What is the boundary interference? Boundary interference is the interference between the two boundary nodes that are co-live across the same CSB. What is CSB? CSB is the context switch boundary, or the one which lies in between the two NSRs. What is an internal interference graph? The answer is D. For each of the NSRs, we have an interference graph which only includes the internal nodes within the NSR, and therefore there are other interference edges, and that is called as an internal interference graph. In other words, this is a part of the interference graph which only shows the interference between the nodes which are completely internal to a NSR. And so finally, what is a global interference graph? The global interference graph, of course, shows both kind of interferences. The interferences across the boundary regions or the boundary nodes, and the interferences between the two nodes which are also completely within the NSR. And also the third type could be an interference between a range which is live across NSR and the ones which is only live within an NSR. So I hope this clarifies how we are setting up the problem for register allocation now that we have found NSRs. Again, we have some nodes which are boundary nodes for live across attributes across the NSRs. Then we have boundary interference, which is between the two NSR nodes. And then the third one is purely internal interference between the nodes which are within NSR. And then finally, we have a global interference graph which captures both local and global interferences. Now, having found this NSR CSB, which is context switch boundary here, and having determined the live ranges, now let us see how we can classify them. In this particular example, the first live range is for a variable buff that we find here. And you can see that it starts here and goes way across the context free region. In fact, could go across the second one also. And this is now a live range which is live across the context free regions. And the node corresponding to this will be a boundary interference node. Similarly, another live range here that we find is LEN, which is also live across the context switch boundaries and is shown here. The third range that we find here is again live across the context switch boundaries, not only on one side, it is also on the other side. The sum, in fact, has been used everywhere. And so this is a range which is live all over the place. All three will form the boundary interference nodes. And again, as you can see here, because they are live across the context switch boundaries, it will not be safe to allocate these to shared registers. They will have to be allocated into private registers, because if we try allocating them to the thread shared register pool, they might hold a particular value, then the context switch may occur, that value will get overwritten, we'll come back here and we'll see a totally different value. And so it will not be safe to hold them in shared registers here. However, if you look at the next live range, TMP1, it starts here and ends here. And this is something which is completely lying within a NSR. It is not crossing a CSB, context switch boundary. And therefore, this type of a range, which is temp1, could be safely allocated to a shared register. Because once the thread comes back here, after a context switch, it can hold that value in a shared register, can use it, and it is done with it. And when it goes to the second context switch point, this range or this particular value is no longer needed and therefore could be easily destroyed by the other threads. We don't care. And in an exact similar way, look at this temp2. This range is also entirely contained in a private manner inside a thread, and so we could safely allocate it to a shared register. And therefore, we can save on the register pressure here. So again, temp2 is entirely contained within an NSR. So before we proceed further, I would like you to make sure that we understand the live range concept very clearly. Please take this quiz to refresh your knowledge of the live range. Here is a simple program excerpt we have shown, and we are asking you to the ranges that are live at each of these instructions. Here are the answers which are marked. For example, this particular point, since S1 has its use here, S1 is live at this particular point, S2's definition is there, and there is some use further down, so S2 is live, and so on. So these ranges are marked to be live at different program points. Please go ahead and check your answers now. If you face any problems about this concept, please go back and review the lessons on the live ranges, how to find them, and how to use that information to create the interference graph, and from there the register allocation. So using our knowledge of live ranges, interference, boundary interference nodes, interference graph, boundary interference graph, and so on, let us now try to build the interference graph for this particular representation. As you know, sum, buff, and len are the ones which are live across these CSRs or across the boundaries, and therefore they form a boundary interference graph among themselves. They are also interfering with each other here. However, the nodes temp1 and temp2 are entirely contained within an NSR. They are not live across the CSBs or the context switch boundaries. So they do not form the boundary interference nodes. So for example here, temp1, which is over here, interferes with all three of these because they are live through here, and so that is why the interference is shown by these three edges. Temp1, however, only interferes with this sum, which is this blue one, and so that interference is also just shown like this. And then of course sum, buff, and len, they are simultaneously live at multiple points, so they interfere with each other. So you can see here that we have a complete interference graph here, and looking at it, we can see just the boundary interference or an interference between a boundary node and a non-boundary node, and so on. And we could also see maybe if there is any interference between the ranges which are within one NSR, which is not there in this particular case because temp2 and temp1 don't interfere. But imagine another entity here which is interfering with temp2. We could have that node, and we could just have that interference between temp2 and temp3, for example. So this IG therefore captures all these different interferences. Now, after building such a representation, next what do? We go to the next step here, which is shown to estimate lower and upper bounds on the number of registers that we need. Now here is some simple formulation which is introduced here to determine the lower and upper bounds in terms of the number of registers that we need. So what we have is total number of threads here. We have the total number of registers, and then we have come up with some estimate of number of private registers we need for each thread. How do we determine these private registers? Well, they could be corresponding to the maximum pressure that we have because of the boundary interferences. Remember, all those buff, len, and sum could not be stored because they are live across the CSBs, the context switch boundaries. And so therefore they must be given a private register. So here that could be 3 registers are required as private registers for thread 1. Similarly, we find out the number of such private registers which are needed for each thread. And then we also have boundary interferences which are between things such as temp1 and temp2 with regard to the other things. And that could tell us how many shared registers we could use for those types of entities. For example, temp1 and temp2 could be allocated in shared register because they are dead at context switch places, and therefore they could be safely held in a shared register. So what we do first is to determine such requirements of private and shared registers for each thread, and then we find out the max requirement for the shared registers, take the number of private registers, take their sum, and our goal is to determine these adjustments of private and shared registers across threads so that the total number of registers that we need at a given time for a given thread remains below the total number of registers that we have. So for example, if we give 3, 5, and 7 registers to 3 threads as private registers, we take their sum here, 3, 5, and 7, which will be 15 registers will be given as private registers. Now we compute the maximum number of shared registers which are available and take their maximum value. And if that maximum value happens to be, let's say 16, then 15 plus 16 is less than or equal to 32, and that will satisfy this register requirement. Very rarely will be the case that the number of shared registers plus the total sum of all the private registers will be below this, and our goal will be to actually optimize this so that it just becomes less than this for the best benefit. So again, this particular equation is very nicely illustrated in this particular diagram, which will help us understand it. What we have done is we have given a certain number of registers depending on the need as private registers to each one of the threads. Remember, the private registers are not to be shared, so we take the sum in terms of the total register pressure for all the threads. But then we also have a pool of shared registers, and each thread may need a different amount of shared register as well. And what we do here is we want to take a maximum of the requirements of such shared registers and take that and that plus the total number of private registers and make sure that requirement is below the total number of registers shown over here. The total number of registers is this. So as illustrated in the last slide, our goal is to balance the number of private and number of shared registers so that the formula is satisfied in a maximal sense, so that the amount of spill that is generated is minimal. So the starting point of this is we estimate for each of the threads a range for the minimal and maximal number of private registers that it needs, and a minimal and maximal number of total registers it needs, and the difference between the two being, of course, the number of shared registers it will have. So these things are found as by simply finding out the maximum number of co-live registers as context switch boundaries. So that is equal to the total number of minimum private registers we'll need, otherwise there will be a spill, because we must hold all of these together in the private registers. And then the min R is the total number of live registers at program points. Again, this indicates the maximum register pressure that is present. So let us test our understanding of live range splitting and what it really helps with. I have an interference graph here between A, B, and C, and it needs 3 colors, as you can see here. A could be given 1, B could be given 2, C could be given 3. That's the only way to really make sure that this graph is colored in terms of normal register allocation. The question is, can we reduce the number of colors? How can we reduce interference? And what is the effect of that? So the correct answer is do a splitting of the live range and insert a move command at the split point. So for example, if we take this live range A and split it in A1 and A2 and connect these two through a register to register move, now we can color the same graph, which is really happens to be a clique of size 3, needs 3 colors to begin with. Now we can do it in 2 colors. How? A1 gets 1, A2 gets 2, for example, B gets 2, and C gets 1. And therefore we can color the whole graph only using 2 colors, but we have to pay a price for the move instruction, and typically the move is a very cheap instruction. So therefore we can apply a similar technique on the boundary interference graph, splitting some live ranges in case we cannot allocate so many private registers. The registers, which could be 3 private registers as shown here, could go down to 2 if we undertake splitting of the boundary interference nodes, such as A. Having done some program transformations, having estimated what is the number of private and shared registers that we need, let us now look at how the inter-thread register allocator uses these estimates, performs program transformations, carried out the register allocation, and so on. For that matter, it is going to invoke the intra-thread register allocation and closely work with it, undertaking some transformations and allocation decisions so as to get the register pressure below the desired value. So the main goal is to avoid spill, and Typically, the solution is found by live range splitting, especially for the boundary interference live ranges to reduce the register pressure. So what we do is, given the total number of register pressure requirements and then the private number of registers that are needed, calculate the total number of move instructions that are needed, and then we do certain ways of reducing the register pressure from inter-thread register allocation. We invoke the intra-thread register allocator, typically to reduce either the number of private registers by 1, again by doing splitting of the boundary interferences, or reduces the number of shared registers by 1, again by using similar techniques, but now applied to the nodes within CSR, and keep doing this activity until there is no change. Remember, this first attempt is to reduce the number of private registers. Only when that kind of fails do we go to reducing the number of shared registers. Why? Because remember, even if we reduce the number of shared registers in a given thread by 1, the overall pressure may not reduce because that is equal to the max of different number of shared registers as shown in the formula first. Why is it max? The reason is you have taken away certain pool as private pool, and whatever is remaining is the shared pool, and unless your maximum pressure meets that requirement, you will not be able to perform an allocation. And that is why this particular order is followed to first reduce the PR so that the summation is reduced. If we cannot really do it, then we try to reduce SR with the hope that the max will somehow get reduced if we are trying to reduce the maximum number of shared registers across threads. So how do we do this? Again, remember the goal here, to meet this constraint in the maximal way, that is when this almost becomes equal to 1. Remember again, the goal is to meet this constraint in the maximal way, that is when this inequality turns into an equality. That is, the total register demand from the threads is exactly met by the total number of available registers. So typically we start with the demand much higher and we bring it in and we just make it equal and then we stop. So we start with the maximum number of private registers and then that of shared registers, and then we'll calculate this particular entity. Is this particular entity holds? If it automatically meets the maximum demand, we'll finish and terminate. If not, we'll go in multiple directions here. So first we'll try to do the reduction on the private registers by 1, because again if we reduce it by 1 for even one thread, this directly gets impacted. So we'll try these different combinations for different threads by invoking their intra-thread register allocators. But at some point we will not be able to avail of this particular reduction without creating tremendous spill. In such cases, we shift in this particular path. And what we'll try to do is, we'll try to reduce the number of shared registers by 1 at each possibility by invoking its register allocator, hoping that that 1 when reduced really reduces this max requirements. And we'll keep doing this. We'll commit the current solution with the minimal cost. And if we still don't meet this particular constraint, then we'll take one more iteration going this way in terms of private registers, or if we cannot because of too much spill, then in terms of the shared register pool. And after iteration, we'll terminate at some point and get the final register allocation done. So as you can see now, the role of live range splitting during this particular process is very, very important, because the way we will reduce this PR by 1 or SR by 1 is by relying on this live range splitting. We'll target spill avoidance and we'll pick the minimal move solution, which is going to introduce the least cost, because spilling the variable is havoc. It is going to cause us tremendous context switch overheads and is not a good idea. So we'll try to undertake the live range splitting, which induces a move but not really a spill. So students, we have seen different techniques to trade register pressures from private to shared registers and so on. And finally, the framework determines the right solution which meets the constraints, tremendously reduces the spills. The spill reduction directly leads to improvement because of less context switching. So by doing this important inter-thread register allocation, what have we achieved? We have achieved meeting the line speeds, the streaming rates, And how did we do that? We did that by getting rid of certain spills. This was a non-obvious solution. Why? Because if we simply divide the number of registers into disjointed registers as private registers, there's no way we can meet the register pressure demands. So what did we do here? We decided to meet those very cleverly by introducing the concept of live range splitting. Why did we do that? So that we can localize these ranges within NSR and taking these then ranges and allocating to the shared registers. So the more sharing we can do is the better, because that way we can meet most demands of the different threads through a single set of pool without privatizing the pool. And this type of solution really leads to huge improvements. Please refer to the instructor's material and read the paper wherein all the results of this, when applied on IXP 2400 series to COMbench and many other benchmarks, they have been shown how effective they are in terms of reducing the spills, effective number of context switches, keeping the efficiency at high level for the execution of a thread, and by achieving their performance limits by keeping the threads engaged by giving them enough number of registers, again via the concept of maximizing shared registers. In this lesson, you should note the following important things. No registers are saved or restored as a part of context switch. Most importantly, register sharing is managed and orchestrated by the compiler. We designate part of the register file as shared and part of it as private. Live ranges undergo intra-thread and inter-thread register allocation. Register sharing reduces overall register pressure, the total number of spills, and of course, the thread execution time is reduced because of less context switches. Let us do an overview of what we learned in this course. We began the traditional computer architectures, then imposed significant changes onto them. The embedded processors need to be fast, cheap, and have low power consumption. We figured out how to change the microarchitectures and ISA to meet this criteria. We did it by improving the hardware as well as the compiler. What did we learn in this particular process? The topics that we looked at were VLIW processors and embedded processors, compilation phases and what is a front end, compiler back end, data flow analysis, register allocation, embedded compiler optimizations for different processors such as DSPs, ARM, and so on. Finally, we looked at network processors and their optimizations. If you are interested in continuing to learn about this fascinating field, your next focus should be security issues in embedded computing. We must know about smart cards, we must know about protocol security, protocol verification, and so on. Thank you for being a part of this class. I tremendously enjoyed teaching it.